yet another edition of the historical seminar series. We're very happy to have Cynthia Rourke today. She is a distinguished scientist at Microsoft Research right here. Cynthia has worked on Cynthia has worked on several topics including computer science, like cryptography, privacy, distributed algorithms. Of course, we know her as the driving force behind, the inventor and the driving force behind the influential notion of differential privacy. But just to give an anecdote, when I started grad school, actually, when I started undergraduate studies, I picked a problem to do research in that was called secure communication. And there was Cynthia in the work with Dolev, Dwork, Watson Young. She had an elegant solution to the problem of secure communication. So I thought, wow, this is amazing. And then I moved on, also in undergrad, to study problems in distributed computing more broadly. Byzantine agreement and consensus. And there again, Cynthia was in this influential work on consensus or Byzantine agreement in partially synchronous networks. This is a great work with Nancy Lynch and Larry Stockmeyer that won her the Dijkstra Prize in distributed computing recently. And then I moved on further and said, how much of Cynthia can I take? And then I started working on non-malleable cryptography, non-malleable encryption to be precise. And there again, Cynthia was, having invented the whole notion of non-malleable cryptography, and that's what she'll speak about today. And then I said, well, this is it. I cannot, no, this cannot be. And then I started working on lattices. Yeah. And there again, was Cynthia, having invented the first lattice-based public key encryption system based on worst case, so with a worst case, average case connection. So hopefully this story illustrates how pervasive and how towering a figure Cynthia is in the fields of cryptography, distributed algorithms, and privacy. I'm very honored to have her speak, and I'm not going to list her awards. You can look it up, but this is really a great honor to have her speak. Cynthia, please.
Thank you for the most generous introduction ever. There's been a lot of work in non-malleable cryptography, and clearly I can't cover all of it. And to tell you a lot about what's been happening in the last 10 or 15 years is not doing you a great service. You already know what happened in the last 10 or 15 years. But what I can try to do is give you a little bit of a taste of what the Gestalt was and what people were thinking about and what I was thinking about when this work began. So the paper that I'm talking about is, of course, non-malleable cryptography with Dani Dolev and Moni Naor. So not everybody's an English speaker, native English speaker. So what is the definition of malleable? The root of malleable is the same as the root of the word mallet or hammer. And it means capable of being transformed, as with a hammer, into another shape or form without breaking or cracking. So sort of being mushed into some other form. Now, in case somebody in this room doesn't know what non-malleability is, or in case somebody listening to the video has never heard of non-malleability, I'll give my favorite example of non-malleability. So the tremendously influential notion of semantic security from Goldwasser and Micali says, roughly speaking, that for every relation R, seeing an encryption of a message X doesn't help us to find a plain text Y such that X and Y are related. In other words, the adversary learns nothing about X just by seeing an encryption of X. And I just want to say that a little bit differently. I want to frame this as the adversary can produce no plain text that is related to X. So my favorite example, the simplest example, is what I'll call the adjudicated coin flip. It's just a thought exercise. You would never actually do a coin flip this way. So there are three parties, Alice, Bob, and the judge publishes an encryption key, E sub judge, and Alice is supposed to flip a bit and encrypt it under EJ and send it to the judge. Bob is supposed to do the same thing, and the judge is supposed to decrypt, compute the XOR of the bits, and announce the result. And the intuition is supposed to be that since Bob doesn't know what Alice is saying, Bob can't force the outcome of the coin flip. And this, of course, is completely false. So in the quadratic residuosity cryptosystem of Goldwasser and Micali, where the public key is a modulus n and z is a non-square with Jacobi symbol 1, mod n, encryptions of zeros are random squares, and encryptions of ones are random squares times z. And here, Bob can force the outcome that he wants. If he wants to force a 0, he can, of course, just send exactly what Alice sends. That will ensure that he has sent the same bit. But that may look fishy, and the judge might get upset, so instead he can multiply it by a random square. And if he wants to force a 1, he can multiply by a random square and then multiply by z. If there was a z in what Alice sent, that z will get squared, and otherwise we have a square. We have z sitting there, a non-square. Okay. So for the purposes of this example, what we want is something that looks just like semantic security with one little twist. Instead of saying that the adversary can't produce a can't produce a y such that R of xy holds, what we say is that the adversary can produce no ciphertext whose plain text is related to x. That is, he can't find a beta such that a beta in encryption of y such that R of xy holds. In other words, he can't take this thing and beat it with a hammer and still have something that looks like an encryption, and and the ciphertext bears a desired relationship to x. Okay. So there are 3 well-known modes of attack for a public key cryptosystem. The first, of course, is no access to the decryption oracle. It's just eavesdropping. This is chosen plain text. The second one we called chosen ciphertext in the pre-processing mode. So the adversary can play with the decryption oracle, can then pick a challenge domain, receive a challenge, and then has to respond to the challenge. And then what we called chosen ciphertext attack in the post-processing mode, where the adversary plays with the decryption oracle, picks a challenge domain, receives a challenge, and then gets to play with the decryption oracle again and can ask anything except the challenge. And then it has to respond to the challenge. So that's our way of saying these things. So with these notions in mind, what was known earlier? So we defined non-malleability in 1991. It's now known by various results of people here and some results from our paper that non-malleability is equivalent to semantic security under these strong attacks. And it's essentially equivalent to indistinguishability with the right definition under these same strong attacks. So what was known about security under chosen ciphertext attacks of any kind when we started to get interested in this problem? And we said Goldwasser and Micali had semantic security against a chosen plain text attack, but not chosen ciphertext. So there's this amazing paper, which is cited in 1982 by Goldwasser, Micali, and Tang. And they talk about the power of a garbage, non-garbage oracle. And what they did was they showed how to exploit the behavior of a system. I have this vague feeling this is not the most current version of the slides. Anyway, how to exploit the behavior of the system. So a response that a ciphertext had failed to decrypt properly would be such a behavior of a system. You send in your credit card information, it's encrypted, something goes wrong, and you get a message saying, I couldn't reach your credit card, try again. They use these kinds of responses in order to decrypt a target ciphertext. And the paper says beautifully, if we want public key crypto systems that are provably secure, the above oracle, like anything else that a user cannot obtain by himself, i.e. without the help of the PKC mechanism, should be suspected of being helpful in inverting E sub A of Y. So they were completely on target. And they designed what they called replay attacks, which are chosen ciphertext attacks, post-processing mode, against the RSA, Rabin, and Goldwasser-Micali schemes to decrypt target ciphertext by extracting behavioral responses to the plain text, getting, for example, the garbage, no garbage bit. So they were completely aware of this issue. They also talked about the lunchtime war CCA pre-attack, where they noted that a chosen ciphertext attack against the Rabin scheme would permit a total break. That is, it would permit factoring the modulus, which would then let you decrypt all future messages that you saw without any future playing. And they asked whether RSA and the Goldwasser-Micali scheme had this property. They said it was not yet known that they had these properties. I should mention here that Boyarsky also showed how to exploit garbage, no garbage information in order to break password authentication mechanisms in a multi-user environment many years later. Okay. 1989. I will mention some things that happened in the interim, but this is a particular unfolding of the story. There was a workshop. It was organized by Joan Feigenbaum and Mike Merritt. And a lot of people were there. Reading through some of these things, I see that I was apparently there. Stuart Haber was there. Moti, Charlie Rakoff. I don't remember whether Shafi was there. You were there. Okay.
Or something like that?
It was physically held in Princeton, but it was DIMAX organized. Yeah. And one of the things that came out of this was a volume of proceedings. The proceedings were published 2 years later, but the proceedings also had a summary of the discussion and the talks and the open questions that Joan and Mike wrote. This is a wonderful summary, and you should take a look at it, and it should inspire you in the future. If you're going to be running a workshop, do what they did. It was fascinating to me. One of the things they did, for example, you can see here at the bottom, is they talked about what were the terms that people were using. These were relatively newly invented terms. Things like authentication, bit commitment, blobs, claw-free one-way permutations, coherence, I don't remember what that was, cryptographically secure pseudorandom number generation, and so on and so forth.
Coherence has to do with self-checking.
Self-checking. Okay. And I should also mention that in addition to sort of the crypto crowd, there were some people from the security community who are no longer attending our meetings and whose meetings we no longer attend, and I think that was a loss. So probably Butler Lampson was there, and certainly Martina Badi was there. Now, during the workshop, Martina Badi gave a talk on what's called the ban logic for Burroughs, Abadi, and Needham, a logic of authentication. They wrote their paper in '89. They got a lot of feedback, which you'll see. They wrote this draft in 1990, so after the feedback, and then the paper seems to have been also published a few more times in SOSP, in one of the transactions, ACM transactions, and in the Proceedings of the Royal Society. But, okay. So this is a protocol, and they're trying to argue about it. And notice that one of the things that happens is party B chooses a nonce, some fresh new random thing, and sends it encrypted under a key that's shared by A and B. And then A responds by subtracting a 1 under the same key. And this is supposed to prove that A is sort of current presently. And in fact, this is what the authors say, that the use of NB-1 in the last message is conventional. Almost any function of NB would do as long as B can distinguish his message from A's. So going back to the summary by Joan and Mike, they point out that a body's talk assumed an encryption function that had the property that given the ciphertext E of x, it's infeasible to generate the ciphertext E of x plus 1, or E of x minus 1. Of course, x plus 1 could be replaced with any simple function of x. And then they say the existence of such an encryption function is an open question. Notice the other open question that starts down here and is discussed up here. They ask about fully homomorphic encryption as well, and they point out how useful that would be. Okay, so that was interesting. And then there was a talk by Stuart Haber, and this is clearly Stuart's own abstract for his talk, because he says he's going to give a formal definition for Chaucer ciphertext security. And he wasn't even thinking about your notion of a crypto system where you just send one message, from sender to receiver, that's it. He's looking more broadly at an interactive method of sending a secure message. And he says that he's going to show how he can use the properties of zero-knowledge proofs of knowledge in order to prove, while waving only one of my hands, and this is just vintage Stuart, that the interactive system proposed in 85 actually satisfies the proposed definition. Now, their definition, if you look at it, is an indistinguishability-based notion. Okay. Now, during the workshop, at various times, 2 different times, I think, Mike Fisher asked about what we would call CCA post security for the interactive case. And Charlie Rakoff asked about it in the non-interactive case. And my recollection is that when Charlie said it, there was sort of a gasp. But it doesn't make any sense given that Goldwasser and Micali and Tong had been talking about it 7 years earlier. But maybe somebody else here remembers. I don't know. Now, as I mentioned, the proceedings came out 2 years later. So we had Stuart's abstract from 1989, and in 1991, they followed up on Mike's suggestion, and they define basically chosen ciphertext attack in the post-processing mode for a protocol for secure transmission, and they called it replay chosen ciphertext attack. And I think the word replay chosen ciphertext attack or replay attack came from the earlier work of Shafi and Poe and Silvio. The proceedings have a definition, but they don't have a proof, and no full version was ever written, and it's not in the Eurocrypt 89 paper. So we don't know whether they actually had, whether there really is such a proof. I couldn't get a commitment one way or the other from the authors. Okay, and again, this was an indistinguishability-based notion.
But it was also an interactive protocol, no?
It was an interactive protocol, and their definition was indistinguishability based. And they're making claims about a protocol that they had written by that point 6 years earlier in 1985 in Crypto 85. Yeah. Okay. 1990, so shortly after this workshop year. Moni and Moti published their public key crypto system, provably secure against chosen ciphertext attack, of course, in the pre-processing mode. And this was a real crypto system where there's just one flow from the sender to the receiver. It's not a protocol, a two-way protocol. So that was sort of what was happening before we did non-malleability in the crypto community. Again, I'm going to go back and point out a few other things, but this is one way of looking at the story. Now, my personal route to non-malleability, so I can't speak for my co-authors, but this was my personal route, is via Byzantine agreement. So I had been studying Byzantine agreement for several years, and in 1982, so kind of just before I got into this problem, or approximately when, Fisher and Lynch showed that in order to tolerate T-faults, you need T+1 rounds of synchronous communication. So even if your system is really nice and communication is proceeding in synchronous rounds, you need T+1 rounds of communication. And then Fisher, Lynch, and Patterson, also in 1982, proved the really beautiful result, saying that no completely asynchronous system can tolerate even one unannounced processor fault. So in other words, it's the nicest possible kind of fault. A processor can just die, or in fact, just get hung up with something for a long time, too long for everybody else to wait, sort of. And then consensus is just impossible. The next year, Michael Rabin demonstrated the power of a global coin. So a global coin for me is God flips a coin and tells everybody in the system the outcome of the coin. That's what we mean by a global coin. What he showed was that there was a randomized algorithm where if God can flip coins and reveal them to everybody, then the expected time was just constant in stark juxtaposition to the T+1 rounds lower bound. That's for the synchronous case. And this focused attention on achieving a global coin, or something close to a global coin. Maybe it wouldn't be perfectly fair, but relatively unbiased. Maybe it wouldn't hit absolutely everybody, but it would reach a sufficiently strong majority. Those both turn out to be sufficient to get this result. Now, in fact, Rabin's result was preceded by a couple of months by Benor's result, showing that individual randomness, no God, just your usual notion of a randomized algorithm where everybody flips their own coins, individual randomness helps in the asynchronous case, takes us from completely impossible to possible. Now, in hindsight, this is sort of a corollary. This is a corollary of Rabin's result. Because if you think about it, suppose each of us is flipping a coin independently. Every now and then, we will all flip the same value. And when that happens, boom, we have a global coin, and plugging it into Rabin's algorithm, things would work. I mean, you need to define some kind of notion of a round because it's a completely asynchronous system, but all of that's doable, especially if you throw in a few more processors.
But you need to know that you all flip the same coin.
No, you don't. It turns out you don't. But that's a property of the algorithm. Okay. Now, okay. So I'm going to tell you a little bit about that algorithm because I love it so much. First of all, Byzantine agreement problem, you probably all know, but remember that each processor starts with its own bit B, BI for processor I, and they send messages and change state and send more messages and so on. And there are two conditions. So every process has to irreversibly, at some point, output a decision bit. And the two conditions are unanimity, all the good guys have to choose the same bit, that's the agreement part, and non-triviality, meaning if all of the good guys start with the same value, that must be the decision value. If the good guys are split, all bets are off, but that's what rules out simply taking the result of God's coin flip, for example. Now, here is Rabin's algorithm, rendered in the randomized algorithms book of Motwani and Raghavan, based on the view of Rabin's algorithm that Benny Shore and I wrote in a survey paper on coin flipping in 1985. And it's actually very simple. Everybody starts with their own value, which is currently, their initial, he called it a vote, BI. And then what did they do? They sent these votes to everybody. So they exchanged votes. They received votes from all the other processors. They looked at the majority value, and they counted how popular that majority value was, and then God flips the coin to choose among two thresholds, both of which are well above n over 2, where n is the number of players. So they compare the count of the majority value to the chosen threshold. If it crosses the threshold, they adopt the majority value if that wasn't already their value, and otherwise they take 0. And again, if the count was really, really large, like n minus t, then they just go ahead and make that their decision value. But they have to keep playing for a couple of rounds afterward, just to help everybody else. So what's going on here? Again, if there's a strong majority value, so here's the count of the majority value from my point of view. If there's a strong majority value, I'm going to decide on that value. And otherwise, I'll look at the coin flip. I'll see which threshold is chosen, the high threshold or the lower one. And these are my instructions. So it turns out that the protocol can be prolonged only if the good processors are split in the sense that some see that the chosen threshold was exceeded, and others see that the chosen threshold was not exceeded. So that requires the bad guys to send different things to different processors. So for example, if the majority value is 1, and the bad guys send zeros to me, I may see that this threshold is not exceeded. But if they sent 1s to you, you might see that the threshold was exceeded. And the key point is that if the two thresholds are far enough apart, then they can do this sort of splitting or foiling of a threshold to only one threshold. And that threshold is chosen after they have committed by sending out their messages. That's when the coin flip happens. And so their chance of having chosen to foil the threshold that's actually selected by God is only a half. And so that doesn't go very long. And then things end very, very fast once you have a non-foiled threshold. OK. So that's why many people who hadn't previously been interested in coin flipping became interested in coin flipping. And then there was an interesting split. You can think of coin flipping in various settings. One setting is the cryptographic one, or the distributed one that we've been working with so far. But the other is a much more abstract version of the problem, which is a full information thing. Each of us flips a coin, let's say, and we all get to see everybody's coins, and we, let's say, take the majority or some other function of these announced coins. We're all applying the same function. And the question becomes, if the bad guys want to force a 0 or 1, can they kind of choose what they're going to say based on what everybody else says, and so to speak, have the last word and force the outcome? So that direction, that full information direction, was followed by Benor and Linial in 1985, and also another paper in 87. And there's a survey paper that I was not able to get my hands on. Mike was traveling, Nati was traveling. But one of the Benor and Linial papers, the 85 paper, I think, says the following. That the problem was considered before, mostly in the framework of the Byzantine generals problem. And basically they say, it's a headache to think about having to deal with only some of the parties receiving some of the information. We don't want to do that. Let's look at the full information case. Now, this led to the famous KKL paper of 1988, which resolves many of the questions that were posed in the earlier papers. By that time, they didn't quite want to confess, apparently, that it was related to Byzantine agreement. And the paper only says that the motivation is discussed elsewhere. So what did they do in the full information world? Benor and Lineal defined the influence of a set. So you have n processors, the influence of or n bits of a subset of the bits on a Boolean function that takes n tuples of bits and maps to 0 or 1, which is, as I said, sort of the probability over the coin flips of everybody outside of S that the members of S have the last word, can throw the decision one way or the other. And they showed a function for which some player always has an influence of log n over n. And they also, appealing to game theory where such notions were already being discussed, talked about multi-round games. They found a multi-round game in which some player has influence at least 1 over n toward 1. There's also a player that would have influence at least 1 over n toward 0, and the paper says, but not one guy who has that kind of influence toward both. Okay. In the KKL paper, they went further, as I said, answering some of the open questions. And they showed that there's always somebody who has a lot of influence, and there's always a small set whose influence is quite substantial, really, really substantial, constant. But in addition to these particular results, they did something else which was very important, which is they really brought harmonic analysis into theoretical computer science. And all these papers, some of which are written by some of you, and others written by your colleagues about Fourier analysis and all these things that you can do with impact on learning and communication complexity and threshold phenomena, approximation bounds, hardness amplification, they sort of stem from here. So that's what happened in the full information direction. It's a tremendous influence on computer science as a whole. How about the cryptography direction? So I've made some remarks about things that people were doing before 1989. So here's some of them. Shor, Goldwasser, Micali, and Averbuk defined a simultaneous broadcast channel. So let's make life really easy, and let's assume that that we are all communicating via an ordinary broadcast channel. Or in fact, each of us has a broadcast channel that won't interfere with anybody else's, but lets us tell the same thing reliably to everybody. Even such a thing doesn't immediately let you solve the coin flipping problem in the adjudicated coin flip. Because one person can sort of wait until everybody else has sent their bits and then choose, his bit to broadcast to everybody, thereby, controlling the exclusive OR, for example. So in the simultaneous broadcast channel, the idea is you want to get the effect of everybody speaking simultaneously. Not in the sense of confusing each other, but in the sense of being independent. So that paper really articulated the independence goal and defined the tool of verifiable secret sharing to achieve this goal. The tool, okay. And gave a suggestion that was resilient to sort of log of n faults. So a relatively small number of faults, but it was, it was a nice concrete suggestion and an important formulation of a problem. Shor and Rabin, 2 years later, did something not quite the same as far as I can understand now. That is, they achieved what was closer to what we now know as a non-malleable commitment. They arranged a situation in which each member commits to a value. By clever scheduling of rounds of communication, They use fewer rounds of communication than the previous paper. But as far as I can understand it now, there doesn't seem to be anything that forces reconstruction when it's time to reconstruct. Verifiable secret sharing ensures that even if the person who dealt out the secret quits or tries to stop things, the committed value will in fact be reconstructed. I don't see that that was true in the Shore and Rabin paper. Let's see. I can't remember. Feldman came up with a non-interactive verifiable secret sharing scheme. Did not need a broadcast channel. Was pretty fast. It relied on something called Crusader Agreement, which is a quick and dirty approximation to full Byzantine agreement. But did use private channels between participants. Okay. In all of this, in all of these solutions, there's sort of a fixed and known set of players. Now, on the internet, of course, there isn't really a fixed set of players. The security guys really understood this because they were worried about sort of people just trying to log in remotely somewhere. You didn't know who was who and whether they were really who they said they were and who might try, people you never heard of trying to log into your system. But somehow that was less of a feature of the work in the cryptography community. So, no fixed set of players, there are no private channels, there's no broadcast channel that talks to everybody. Anybody can be doing anything with anybody else at any time. So in that sort of a situation, how can we get independence? And this brings me to 1991. So I sort of think about this as cryptography in vivo, that is in life, rather than in vitro, which is in the test tube. When you think of independence, of course, there are several settings. There's the encryption setting. So you have a sender and a receiver. Over here, you have some other sender, possibly the same as this, possibly just somebody who's colluding with him, and some other innocent receiver. The first sender sends a message alpha, the second one is sending beta, and we want somehow that alpha and beta should be independent. So things like this come up in contract bidding, and in general, it's a sort of encryption is, as you know, a fundamental primitive. In commitments, which are a key step in zero-knowledge proofs, and also a generally very, very powerful primitive, you know, sender and receiver communicate, sender prime and receiver prime communicate, an adversary can be a man in the middle. And again, we want to achieve that what is said over here is independent from what is committed to over there. And the same thing could be true in other kinds of zero-knowledge interactions, zero-knowledge proofs of knowledge, zero-knowledge proofs in general. What gets proved over here should be independent from what's proved over there. So these are all a sort of simulation-based idea. Whatever you can do in this big system, you should be able to do, even if you lop off the left half and it goes away. And these were the kinds of firsts that we had in the DDN paper. So first of all, we had a definition of non-malleability that emphasized the commonality of these problems. I don't think they were quite understood to be all the same thing before. We gave a public key cryptosystem that's non-malleable and, of course, also semantically secure against the chosen ciphertext post-processing. And we used just about every tool under the sun that existed at that time. We used semantically secure encryption, one-time signatures, universal families of one-way hash functions, non-interactive zero-knowledge proofs. Okay. And the cryptosystem had the property that it was immune to the garbage, no garbage oracle because it was possible, looking at the ciphertext, to tell by inspection with no help whatsoever whether or not it was a valid ciphertext. We also defined and constructed, much more simply, private key crypto systems that are secure in this way. We gave a non-malleable commitment scheme whose running time was number of rounds of communication was logarithmic in the security parameter, and it was based only on one-way functions. And we gave a compiler for general non-malleable interactions that took zero-knowledge interactions, that took ordinary zero-knowledge interactions and spat out a non-malleable version. At some point, we included, in a fuller version, we included a lot of the relationships. So if you have two notions of security, semantic security and non-malleable security. And 3 kinds of attacks, that gives you 6 classes. And we understood the relations between all of them except these 2. And that was provided at some point by Bellare, Desai, Poincheval, and Rogaway. I'm sorry, I forgot the year, but it comes up again later. Okay. So going back to the Naor-Yung construction for CCA pre-processing, the public key was just a pair of ordinary semantically secure encryption keys, E1, E2, together with a long random string. Encryption, to encrypt, you encrypted the same message under both keys, and you used the random string to give a non-interactive zero-knowledge proof of equivalence. Again, anybody could tell by inspection whether it was a valid ciphertext or not. And then on decryption, if it was valid, then you decrypt using either ciphertext. Okay, and of course, this is malleable if either of the EIs is malleable. So what we added was the sort of freshly chosen by the sender for each message one-time signature scheme. We used Lamport's scheme, but we chose it anew each time you wanted to send an encryption. And that was used to authenticate the ciphertext. So now instead of just having a pair of ciphertexts, we have several pairs of ciphertext. We use the verification key of the one-time signature scheme to choose between for each pair between which to choose for each pair which one we were going to use for an encryption. We encrypted under these selected things. We gave a zero-knowledge proof of that everything was done correctly. And this basically boxed the attacker in the following way. If the attacker used the same one-time signature scheme, then since he can't forge, he can only send the same message. If he uses a different one, then there's going to be at least one position, one bit that's different in the verification key, which means that maybe for the original message it was encrypted here, and now the guy is on his own and has to compute an encryption of his mauled message over here, and he has no guidance. This is a completely fresh crypto system. So this idea of being forced somehow or other to do something on your own every now and then is, of course, what pervades all of the non-malleable things that have been built. Now, the popular reaction to this was talking about the attacker. Who would do that? And I mean, they didn't even say those wacky cryptographers. They said those wacky theoreticians. You know, they sort of dripping with scorn. 7 years later, Victor Shoup, trying hard. Why chosen ciphertext security matters. He's still arguing. There was a panel discussion at a TCC that was held at MIT, 2004 maybe? A panel discussion. Same discussion, same issue. This is, as you all know that that Kramer and Shoup have a crypto system that only takes 2 exponentiations instead of 1. So it's really very, very cheap. Oh, we couldn't possibly pay that much, was the sort of thing. And Silvio said, you know, there's such a thing as best practices. Someday something's going to be broken, and there's going to be a court case. And the judge is going to say, where is Kramer? Where is Shoup? Okay, so what did happen in 1998? Bleichenbacher attacked. Bleichenbacher used the garbage, no garbage oracle and the malleability of the PKCS1 implementation of RSA to break a real live running crypto system and decrypt messages. And he did it pretty fast. Also, what happened in 1998, Kramer and Shoup came up with a truly practical solution. Then some other things happened. There was a lot more, there was a bunch of definitional work that started happening. There were advances in new models, so non-interactive, non-malleable commitment. And I mean, I'm not, this was a real search. And it was looking for things that had happened in 1998. Apparently, we published a tech report maybe that of the full version. But, you know, lots of stuff happened. And something else down here, which we'll see in a minute. Okay, so directions of the definitional work. Well, there was a lot of examination of relations among indistinguishability versions of concepts that we defined in DDN. Everything that we defined was very much simulation-based. And that was really our motivation. It's almost odd for me to think about it as an indistinguishability question. But Bellari et al. Came up with some indistinguishability versions of what we had done. They, as I said, they resolved that open question, improved some other things. And then I guess Bellari and Sahai in 1999 and 2006 sort of showed that, these are all talking about the same thing. And they defined some notion of parallel chosen ciphertext attack. But basically, these are all the same thing. And then there were some other axes. And of course, I can't do justice to what all of you have done. I'm just mentioning a few things. There were other axes of definitional work, very, very careful nitpicking, good nitpicking on the definitions by Pas, Shalat, and Vaikunthanathan. Looked at relationships when you have receipts of multiple messages, whether the system allows invalid ciphertext to be generated or doesn't allow, and so on and so forth. Okay. There was also, after that, quite a bit of work building other encryption schemes that were non-malleable under these post-processing attacks. Canetti and Goldwasser did the threshold Kramer-Shoup, and they had some very cool way of finessing the valid versus invalid situation. When something was invalid, they would just not tell you this. They would just give you a random value, and that was a key point. There was non-malleable identity-based encryption, but there's also getting strongly non-malleable stuff from any identity-based encryption scheme. Then there are non-malleable lattice-based encryptions that have worst-case, average-case solutions. There were some results about black box relations, and I'm sure there were other papers. I saw other papers, but I ran out of time. I forgot to include one of them. Just general, how do you build non-malleable, efficiently, quickly, how do you build non-malleable schemes from semantically secure schemes? Another direction that I found interesting, and which in some sense traces back to that work or that discussion of the Burroughs, Abadi, and Needham work, non-malleability, and of course, whenever I'm saying this, I'm using it as shorthand for non-malleability under CCA post attacks, shows up in some interesting work in formal methods. So probably all of you are aware of the Dolev Yao work that argues about protocols that use encryption. We've talked about the band logic. there was sort of this formal reasoning in those communities, and that formal reasoning has nothing to do with complexity theory. And of course, all of the malleability stuff has very much to do with complexity theory. It has very much to do with the actual algebra and properties of the system that you're using, and how you can exploit these in order to create related ciphertexts. So there was some attempt to start to bridge these formal and computational views. Some early work there by Lincoln, Mitchell, and Shedroff, Abadi and Rogaway, and so on. The ones in red are the ones that explicitly call out the usefulness of non-malleability. And for example, in the Lincoln et al. Paper that says, the gold standard is semantic security, but for the purposes of reasoning about authentication protocols, it seems that non-malleable schemes make more sense. Non-malleable that definition makes more sense. Okay, so that's kind of what I wanted to say about encryption. I have a bit less to say about commitment because we talked about a long time. But there were some really interesting milestones. First of all, there was Barak's constant round protocol in 2002. Now, this follows, and I guess is inspired by, his amazing breaking of the
black box.
Thank you. Breaking of the black box. He proves zero knowledge without using black box, and he does something really, really interesting, where you sort of end up anticipating the message that the verifier will send, and you use this. Of course, you don't do that in real life, but you use that in the simulation. So what did he do? He sort of formulated a notion of independent string protocol. So, and he paired that with work on non-interactive, non-malleable commitment. And there was a lot of work on non-interactive, non-malleable commitments. Okay, so of course, when you have a non-interactive blah, 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 there's usually a shared random string. So what Barak did was he had a protocol in which a random string would be chosen here that's going to be used as the CRS, and another one chosen over here, presumably. And it ensures that either they're the same or they are completely independent. And from that, he's able to ensure that what gets committed to over here is either the same as this or independent. In 2005, Pass and Rosen came up with the first constant round protocol for non-malleable commitment that relied only on standard collision-resistant hash functions, so weaker assumptions. And a nice thing about what they did is that in DDN, we used non-malleable commitment in order to get non-malleable zero knowledge. They did the other way around. They used non-malleable zero knowledge in order to have non-malleable commitment. Also, in a different paper in 2005, the same authors studied what they studied concurrency, which is, I guess, something that we had raised a little bit in DDN, but we didn't completely address, where you have lots of left and lots of right interactions. And the goal is to avoid joint dependencies between more than a single pair. So you could have more complicated things. And there was various papers that get faster results or results that use weaker assumptions. In particular, there's a 4-round, very simple, non-malleable, concurrent, non-malleable commitment scheme of Goyal, Richelson, Rosen, and Wald. And it's 4 rounds from any one-way function. In zero knowledge, people looked at non-malleable zero knowledge proofs of plaintext knowledge. But another direction is in concurrency. When we talk about concurrent non-malleable commitments, it's just that picture that I showed before. It's really the same problem, but it's more complicated. Here, there's a different problem. With zero knowledge, there's a different problem. Basically, non-malleability addresses soundness in a zero-knowledge proof system. But it doesn't guarantee that if a prover is proving to multiple verifiers that the entire interaction remains zero knowledge. That is, if all of those verifiers got together and pooled everything they knew and coordinated their questions, maybe they could have learned more from this prover. So concurrent zero knowledge addresses this. And Amit and Moni and I identified this problem, and we gave a timing-based solution in a very weak timing model. We had something called an alpha-beta assumption, which says that, I guess, if all things, that messages would take time at most beta to be delivered, and that nobody could react too fast, or you could wait to be sure that no one reacts too fast. And those timing assumptions can then be used to avoid some very unpleasant interactions that would harm the zero-knowledge nature of the total interaction. Also spun off from that work, we talked about deniable authentication, and then later Moni defined and achieved ring authentication, which allows verifiability and deniability for any member of an ad hoc set or a ring. Now, another thing that happened in '88 is that Amit and I came up with a very simple extension of this use of timing, which was that
Kindergarten.
1998. I was a little young at that time.
Sorry, you're right. Okay, 1998. Is that we came up with a very simple protocol where any two people who decided at any point in time, independent of anything else that was going on, that they would like to start communicating with each other, could run a very tiny, like 3 or 4 round protocol that was timing based, after which they never had to use timing again. And it seemed to me like an incredibly reasonable setup protocol. Very, very low overhead, no special coordination, just nothing. And then after that, everything became straight line simulatable, and there were never any problems with zero knowledge. The first vanilla solution that doesn't use timing of any sort was Richardson and Killian. And of course, that got improved, and there were faster things that used fewer assumptions and so on.
Cynthia?
Yeah.
This work with Amit, was it constant round, or did it take more?
It was constant round, I think. Yeah. It was like 4 rounds. Really nothing anybody should get very upset about. I mean, the problem with the timing-based solutions here is somebody could argue that you had to slow down everything, the whole interaction. Whereas here, you only had to slow down your particular pair once for a constant number of steps, and then you were done. Okay, 2001. In some sense, going back, in some sense, what we were moving toward here was a general notion of plug and play. We had identified 2 kinds of problems, remaining zero knowledge under concurrency and achieving independence. And indeed, in 2001, Canetti came out with universal composability, where you have an unbounded number of concurrent protocols in arbitrary, adversarially controlled network environment. Now, it's well known that this is not achievable in general, and there have been a few, sort of 2 directions that people follow in order to cope with this fact. One is relaxed simulation, quasi-polynomial time simulation, maybe use of timing, input indistinguishability. Another branch of work looks at trusted setup, like a common random string or a not so good common random string or collection of random strings. And there is a really nice paper that that talks about universally composable puzzles, I guess. And it gives a unifying framework for the relationships, these relaxations and the trusted setup approaches. And they show that you can do this based on they can build this from any standalone non-malleable commitment scheme. So you need very little setup and then a simple, then any standalone non-malleable commitment scheme. For example, the really beautiful 4-round one that I just mentioned. And they address the static case. In the static case, their work takes constant overhead. By static, of course, I mean that the adversary chooses in advance whom to make faulty. There has been follow-up work in the dynamic case, but it's still slow as far as I know. Finally, there's been a lot of work on non-malleability with other flavors and contexts. So really interesting direction is the targeted malleability work of Bonet-Segev and Waters, where you permit mauling to specified functions of the original message, but you rule out everything else. You can imagine that there are a lot of uses for that. There's the non-malleable code work that, sorry about the spelling mistake. So
That's correct.
equals is not spelled correctly on the next line. So something is encoded. Something's encoded, it gets tampered with, something gets reconstructed, and what you want is that the reconstructed thing will either be the same as the original or completely unrelated to it. And finally, the non-malleable extractors, which controls the relationship between the extracted randomness when one seed is chosen as a function of the other. So I'd just like to suggest 2 future directions. Exploit the attributes of the physical world. This is what we did with the timing work. Everybody has clocks. They're really, 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 really good. Use them. Don't tie your hands behind your back. Find other attributes of the physical world that you can use that will simplify your cryptography. Use it. There's no point in being a purist.
So, but you kept on saying people shouldn't have been upset, but I guess the people were upset, so.
They were wrong. And the other thing that I would say is find applications of these primitives to real-life problems and make them stick. Insist that things that you know how to do the right way are actually done the right way. If somebody says to you, there are no applications to commitment, there's no applications for non-malleable commitments, find really compelling real-life applications and insist that people use it. Thanks.
Questions for Cynthia? No questions.
Question.
Yes.
Do you have an opinion about using the word mall to mean
It is, okay.
trying to prevent?
Etymologically speaking, it is the right word. It is. It's not a pretty word, but it is the right etymologically speaking. Thanks.